In this video, I'm going to talk about power factor and significance of power factor in our power system. Okay, so power factor is nothing but we indicate with the cos theta. What exactly it indicates? So if you have resistive load, it only opposes the flow of current. So the voltage waveform and current waveform, they both, for resistive load, if you look at the voltage waveform, current waveform, they both are going to start at the same time and at the same time. So there is no phase angle between V and I for a resistive load. Okay, where when it comes to the RL or RC RL is a inductive load plus resistance, capacitive load plus resistance, RC load is. Here what happens, inductor oppose the rate of change of current, so current is going to start a little bit late, so there is always angle between the voltage and current. So this is current and voltage. Same thing here, capacitance oppose the rate of change of voltage, so voltage is going to start but the current is going to start little early. Okay, so when it comes to RC circuit, RL circuit, there is always some phase angle between voltage and current. So cosine of that phase angle is nothing but power factor. Okay, so theta is angle between voltage and current. So for the pure resistive load, what is the angle? Pure resistive load, that angle is 0, cos 0 is 1. So pure resistive load will have unity power factor. Unity means 1. Okay, indicates resistive load. If you see a unity power factor load, that is a resistive load. Now, so the cos theta value always between 0 and 1. Power factor is always between 0 and 1. And cos theta value is obviously minus 1 to 1, but here there is no negative power factor. Power factor is always between 0 and 1. No unit. Power factor does not have any unit, but we must indicate it's a lagging or leading power factor. That lagging or leading, it's not a unit, it just indicates what kind of load we are connecting it to. So is it a capacitive load, inductive load, or resistive load, something like that. Okay, so if it is a lagging power factor, say if I say power factor equal to, say, cos theta equal to 0.7, it doesn't make any sense. You have to indicate whether it is lagging or leading. Lagging, usually say lag. So that indicates that it's a inductive load. Okay, so that lagging indicates inductive load. Why it is lagging? Because we always take voltage as a reference. So voltage is going first, current is going next. Current is always lagging here, so we call it as a lagging power factor. Same thing with RC of cos theta. So this is inductive, and if cos theta equal to 0.7 leading, okay, that's a capacitive load. Okay, current is going first, so current leads the voltage, so that's the reason we call it as leading power factor. So that's what lagging and leading indicates. Now cos theta equal to, the formula to find power factor, cos theta equal to R over Z or P over S. You can use any one of these two formulas. If we know the active, P is the active power, S is the apparent power, R resistance, Z is impedance. So if you have impedance Z equal to 3 plus J4, so we know that 3 is resistance plus J4 is inductive reactance, JXL, right? JXL always have plus. If it is JXC, you see always minus. Okay, so if I convert this into polar format, so 3 plus J4 is rectangular format. If I convert that into polar format, I'll end up with 5 at an angle of 53.13. Then power factor of this circuit is nothing but cos theta, where theta is same as this. Okay, or you can say R over Z. Here R is 3, Z, just take the magnitude. This is Z basically. 3 over 5, which is 0.6, lagging. The same way cos 53.13 is also 0.6. I'm saying lagging because I can tell this is an inductive reactance. Whenever you see inductive reactance, that's a lagging power factor. If it is capacitive reactance, then that is leading power factor. Okay, and as I mentioned, unity power factor indicates it's a resistive load. Okay. What is the importance of a power factor? Now, I will show you with a simple example here. So here is a generator. The generator is generating 10 kV, a single phase generator. Okay. Um, Usually the voltage generation is 11 kV, 13.3 kV, something like that, all over the world. A single phase system or three phase system. Um, I'm sorry, mostly three phase system, 11 kV or 13.3 kV, something like that. And if the voltage is that big, most probably that's a three phase generator. Very rarely you see single phase with that high voltage. For calculation purpose, I'm just taking 10 kV. Okay, that generator is assume that that's a little bit far away from the load. So load center is 1 megawatt, and assume that the power factor is unity. Whenever I say unity, I don't need to indicate lagging or leading. Lagging indicates inductive load, leading indicates capacitive load, but here one indicates resistive load. So okay, whenever you have one, you don't need to say lagging or leading. Now every conductor is going to have some resistance, rho L by A. Rho is the resistivity, L is length, A is cross sectional area. Assume that the generator is like probably 1 mile away from the power plant, 1 mile away from the load center. Okay, so that conductor has assumed that that has a 1 ohm resistance. Now what is the current passing through it? When it comes to the AC, P equal to VI cos theta. In DC, we have only one formula, but when it comes to AC, P equal to VI cos theta. That's the AC power. Power in AC circuit, VI cos theta. So here, P is 1 megawatt, okay, which is 10 to the power of 6 watt, over V cos theta is 10 kilo, so 100 ampere is passing through that, uh, passing through the wire. Okay, now since that line has a resistance of 1 ohm, there are power losses. Those power losses are 10 kilowatt. Okay, I square times R, 100 square times 1, which is 10 kilowatt. So 10 kilowatt of power wastage in that line, transmission line. What does indicate? What does it indicate? It indicates that we are wasting this much power in the transmission line. Wasting in the sense the transmission line is going to convert this much power into either heat or light. I mean, you don't see light on the transmission lines or distribution lines. It probably it's going to convert that into heat. Okay, so that's the reason those electric wires are a little bit hot. Now assume that power factor is reduced to 0.7 lagging. So what do you mean by cos theta is 1 and cos theta is 0.7? So if you look into your home, basically here you turned on everything resistive load. So what is the resistive load at your home? Your dryer is resistive load. Okay, wherever you see rotating parts, it's a inductive load. Dryer has rotating part, but at the same time the heat it produces is very high compared to the power consumed by that rotation. Okay, so I'm assuming that motor might be like half HP, which is 300 watts. 743 divided by 2, and but probably it's taking around 3000 to 4000 watt to produce that heat. Okay, so compared to 4000 watt, 300 watt is less than 10%, so we can take that as a resistive load. Okay, now what is the other resistive load? You can see your iron box is a resistive load. Whenever you're ironing your clothes, that's a resistive load. Your What else in your home? Most probably your electric stove is a resistive load. Okay, now you turned off your resistive load. Now you turned on something else like your pump, water pump. As I mentioned, wherever you see electrical motor, that's a inductive load. Okay, your washer is resistive load, sorry, inductive load, because it's not producing any heat, but it has lots of rotation. So probably the motor they used it there like 1 HP, 1.5 HP, 2 HP motor. Same thing with refrigerator. Okay, your AC is inductive load. So you turned on your um, inductive load. What happens when you turn on your inductive load? Power factor is going to go down. Assume that that's 0.7 lagging. By the way, your home doesn't consume 1 megawatt in the US. Most probably, if you turn on everything in your home, probably your maximum load is around 20-25 kilowatt. Okay, so, but I'm giving you an example here. Now, since power factor is low, 0.7 lagging, then I equal to P over V cos theta. Now your current is increased to 142.85 ampere inside the wire. Now the line losses increased to 20 kilowatt. Previously it was 10 kilowatt. Now your line losses increased to 20 kilowatt. Okay, so who is paying for that extra 20 kilowatt? You're not paying. Theoretically, practically you are paying if you look into your energy bill, but utility company has to spend extra gas at the generator side to produce this extra power. At the same time, previously this power line is consuming only 10 kilowatt. The heat produced by this line is less. When it is consuming 20 kilowatt, it produces lots of heat. That means the life of that line is going down. Okay, so with low power factor, the utility company has to spend more fuel on the generator side, and at the same time the life of that power line is going to go down. So that's the reason utility companies want us to maintain high power factor. Okay, now at the same time, whenever your power factor is low, that means it requires reactive power. Remember in the previous video I showed you a Coke bottle. So the liquid, pure liquid, is active power, and the foam, when you shake it, the foam is created, right? That foam is reactive power. So transferring reactive power inside this wire is also difficult. That's another challenge utility companies doesn't want to go through. Okay, so that's the reason what they do, they want you to maintain high power factor at the load side. If your power factor is low, usually most of the time they install capacitor banks in your neighborhood, nearby your neighborhood, somewhere on the power lines. So that's the reason you might see in some of the poles have a capacitor bank. Okay, so that capacitors always produce reactive power. So basically what we're doing, say if I have a capacitor bank right there, so here power factor is still, it is close to 1. So when it comes here, this capacitor bank is producing reactive power and inductive load is consuming reactive power, so that they balance out each other. Okay, so capacitor load always produces reactive power, inductive load always consumes reactive power. So that's the significance of power factor. Thank you.